Welcome to the second part of the Elm Goose-driven tutorial. No geese were drawn in the first part, and that could happen that in this part no geese will be drawn as well. Still, we are continuing with implementing different types of renderers. And the next type in our list is actually the list of things. We already have the type definition, but just no. Let's define the renderer. Sorry. List no geese. List renderer. And it will be the renderer for the list of items. And the same as before, we'll need the renderer for every item. But let's do it a bit later. So those are items. And to draw them one after another, we'll use the recursion technique. I hope in this tutorial, and I'm not explaining a lot, but I'm trying to give examples of different approaches and things and the type system. Hope it helps. In functional programming, recursion is the often used technique to process some sequential things. Let me give you an example, and maybe that will be easier to see why it's useful. So we actually can take from the list of items, we can take the first item and leave the other ones to be rendered later with the same function, because this function accepts lists. At this moment, our renderers return lists, so it's good for us. Okay, so now we will add the renderer A, and we call it item renderer, and we render the first item, the first one with it. Oh, okay, it's still the list. And then what we do, we concatenate it with the other items rendered by the same function, but called with the rest of those. And what the compiler tells us that we don't have the case for the empty list. And this is important. The first rule of recursion is to have the terminal rule, so that when you go deeper and deeper, so that you would stop at some point, and there has to be a stop. So the compiler tries to look for these things and keep you safe from the infinite recursions, which in very, very rare cases could happen, but those are really rare. And usually it's not with those kinds of functions, but with asynchronous stuff and the things. Okay, so when the list is empty, when the source list is empty, we also return the empty list of renderables. And we may use it already, but it will not be really illustrative, because, for example, unit renderer, because our items are placed one over another, like that was with the with those face palms. So here we have probably 3 face palms, one under another. And this is the reason why we will again change the specification of the renderer just slightly, but we will do it several times more. But it's also the usual process of development. You specify the very simple types, and you use some simple variables in functional programming, and then you complicate things, make them more complex, and just keep them compiled. Okay, it's not always that easy, but still. Okay, so we will need to pass the position where to draw uh, the every new element. It isn't position, but the point. But it's actually the alias for the tuple of 2 floats, I suppose. Now again we have the case when everything broke, but the fix should be easy. No, this time maybe not that easy. Okay, let's do it. Since the canvas point is the same as float and float. Oh no, this is the definition of the renderer already. So we have this in the type specification. So we still may replace this and put the string instead of the a type variable, and it will be the same. So we get the x and y as the position where to draw things. yes, this time a bit more complicated, since now every render requires position to be passed. So in this case as well, we may write it shorter actually. But we won't. In this case, the position is after this argument. So it is the next argument. Again, following this specification, this type specification is the next argument after the renderer. So we pass it here and here, and we get it here before the value, every time before the value. Every time. And here, and here, and here. I try to keep the renderers up to date to comply with the type specification, so that we would use them still in our more complex examples. And actually the first call, the root call, we have to specify the position as well, and it's for the moment 0, 0. Now, in every renderer, we have the position, which we, for the moment, just pass inside the inner renderer. What do we want now is to display the list, like the item, the comma, the item, then the comma, and so on. For that, we will need to know how many we know how many items there are in the list using the length function. Oh, and also we will need some variable, which is just the function of 0 arguments. Let's say it's 45 for now. We will not calculate a lot, and we will not calculate the width of every different item. We just suppose that they all have the same width. Multiplied by item width. So this is the block let in, and case is the inside the in part of this block. Let's move this part that renders items. Let's call it render items here, so that we may reuse it. So for now, we have the render for the string. We have to position it somewhere. For example, I just use this number because, and it's not the item width, it's line height, because these strings on canvas are displayed. The baseline is where y is equal to 0, so we have to put it a little bit down. Let's see, are we able to? No, why not? Why don't we see anything? Oh, actually the position is not used. Yes. Yes, now we use the position, and here we have the opening bracket. Then we want to render items. Let's say we move the X point a bit further after the bracket, and we keep the same baseline here. Okay, so now our items renderer here accepts two arguments. It's local pos. We cannot name the arguments the same, so we need a different name, and some inner items. Let's name it inner items. And now we will work with inner items here. It still doesn't look good, I know. And we finish that all with a closing bracket, which should be located after all the items we have drawn. So we move it by the distance. Why do we have several brackets now? Oh, because here we use the render, the list renderer itself. So it calls for every item. It calls this function. But what we actually need is to call this helper and to pass the local position to it. And we don't need the item renderer there because it is the same on every cycle. And let's call this not other but the rest maybe. So I suppose the facepalm imagery is a bit wider, so let's make it 65. Now we need to use the local position here as well to render the item, and here it is, actually where we expected, but we are not moving the position yet. Let's extract the X and Y components of the position, since the point is just the tuple of two numbers, and keep it the same for now. Also, I want to render the comma between the items, and it also should be for now the same point, comma. And now we align the things. We need to move comma after the item. In this case, it is too far away. Let's say we will not do smart calculation. We'll just do like these things. Just move it a bit down. Yeah, cool. And the other items we also move by this item width and plus. We don't need any plus because the comma occupies the place for them. I'll show you what is here, what we have here. So there it is. We have items and commas and brackets. Yes, we have the tail comma, and we won't get rid of it because it will complicate our code. We don't want it. And just to say how it can be done, just by passing the index of the item inside and determining if it's the last item, then we don't show the comma, and that's it. Let's render something a bit more complex. We have these helpers from the list type, like repeat 10 units, or we can do 100 or 1000. It is, we don't see the other end, so it can be as many as we want. Let's change it. We haven't tried yet the combination of maybe renderer and the string renderer. Yes, and let's say it's just x, just x. Let's say it's a smile. And for example, let's make it the list where some items are just and some items are not. So that's it, a little bit off edges, but we get it right, seems. And again, if we replace this string renderer with the unit renderer, we'll get this the same. Everything is good. And let's use the either renderer, and this time it will be string renderer here. So the left values should be units and the right values should be strings. And again, everything is working as expected. So what's next? Let's try two-dimensional grids. And that could sound complex, but actually it's very easy. So now our renderer, we call it grid renderer, will take the lists of lists. Now it will turn out that it's not that easy. I'm kidding. Skip the position for now. And we get the items here, which is in this case not a list, but a grid, a list of lists. And what do we do? Since we have to return the list of renderables, not two-dimensional list in this case, this is what we return. We just have to put the lists we have here in the proper position by y coordinate. So what we will do is take these items and walk through the list with the index, the same technique that would help us in the previous case, but we didn't do it. And here we pass the lambda function, and so the index of every item in this outer list is the index of the row. So we will use it for our advantage and call the list renderer for the moment at 0. We convert the index to float because the points are float and the indices are integers, and multiply it by it should be item height. Let's name it that way. Height. That'd be also 65. Multiplied by item height. But what we get now is the list of lists because we just replaced every this list with the rendered list, and in this case we will use the technique. Let's make it that way. Elm list, it's in the core. So we need some function that accepts the list of lists and returns the lists combined. And what we do, we just search through the specifications, and eventually we will find it, I suppose, because it should be there. Oh yes, yes, here it is. In functional programming, why these type specifications are very useful, because you may Google for them, for example, in Haskell, and there are also websites similar to that in Elm. Let's see if I can show it to you. So yes, this is the website which searches for the things using their type specification. Let's try it. So the first result is our concat function. This is useful also because with the time you will find out that I forgot to pass the actual row here, and something else. Oh, the item renderer. Let's split it in lines. So that's it. Yes. So there is a deterministic number of functions which satisfy the specific type, and usually there are not a lot. I don't know if I use the term deterministic properly in this case. Let's leave it that way. There are not a lot of functions, variants of functions with different types, so that actually helps because they do similar things usually. Okay. So I suppose we have our grid renderer now. That easy. So now instead of lists, we have lists of lists. And I don't see the result. Why? We have shifted the Y position. Oh, okay, we didn't use the position in the list renderer. So we need this XY, and we need to pass the X here and to do this way, and no, Y plus 45 again. So there is our grid. Example, we change the cell here, and it changes as well, and the cell here, and it changes as well. How could that be useful? I don't know. Well, we yet to discover. Also, we may create a huge grid. Let's try that. We'll use the list repeat function, which just repeats things. But now we need to create a grid of lists, so we use command list repeat again and use this fancy thing here. So there it is, the grid. Let's try to change it to something if it has the odd index, we will show the right value, and if it has the even index, we'll show the left one. So for that to work, we need to pass, in this case, we read the expression from right to left, since those arrows. So first we create the instance of left with the unit inside, then we repeat it 10 times and get the list, and then we map it with the index. And so if index, I suppose it's this way, the remainder of division. I don't use it often, so I don't recall. Then left unit, else right string. Okay, it wasn't. Then if it's not, then it's, but you see, still we have some results. Let's remove the commas. Let's command them. Yep, that's better. There is another function, is mod by 2 x. Yes. So we have the unit items and the left, which are left items, and the x items, which are different. You may ask, also, by the way, we may have here anything because we replace the value in this indexed map. So we may just pass the unit here and it will still work. What if I haven't tried yet this as well? If we use the list of things here, because why not? And now we need the list render here, but it contains units, so we pass unit renderer here, and we got something. So those are still arguments of the grid renderer function. This is the first one, this is the second one, and this is the last one. Those things are just blocks inside and inside. This is also a block, and every block should return something. So you couldn't do something like that because there is no value for the else case. And this way we control that our application has no uh, nullable values. So always we return something, and this is why also this unit thing is useful, because you can replace it and use it like the stop for something to return. So we got lists here. Inside lists, something happened, but it worked. We want investigate why it's looking this way. But still, let's no, yeah. Mm. So what is next? Uh, maybe you see it's coming that we will replace all these face palms and uh, everything with something prettier a bit later, but all those renderers are still with us, will be still with us, and they are easy replaceable, like pluggable. So uh, the point of this tutorial is to uh, demonstrate how interchangeable are all those things. So the next one, and probably the last in this section, we had no renderer for the integer values. Let's this is not the last one. I just thought that since we have something for the strings, and it's not, it's fast to write it. So it's the renderer, and the same we have get the position and the number, and we just use the string renderer, but convert the number before passing it. And I have some code ready for this to replace it with the number emojis. So that's it. This is the same as we'll do this way. And this could demonstrate you that we may replace every thing like the token with the expression. Those are Passion arguments are actually expressions. So here we may have something like if n equals to 0, then position, or are, for example, 0, 0, and we cannot return something other than the point from here, because every expression should evaluate to the same type on every end. So, and we could also use lambda here. No, in this case we can't, because it's not the function, which is the argument, but different others like let x be 42 in position. We just return the position and create the variable which we don't use. But why not? This is still compiles, because those are just blocks. Okay, and it took a bit longer for the integers. Let's try it and show the index, for example, because why not? And index is an integer, so as you may see, those are the numbers. And we may always, again, this expression evaluates to either type we used here, so it is the same on all the ends. But let's just show the index every time. So here it is, that easy. Also, while I'm here, I wanted to make this generic let's name it generic renderer. And now we just show nothing in both cases. That's a generic. And also to make it easier to read, y r l value, r value. So these are different things. L value, r value, and here we don't use it actually, so whatever. Yes, now it's good. The last structure in this section is the tree. Not like, I think you know which kind of tree I mean. The one that the digital, I don't know, the programmer's kind of tree, which splits the which has some root and splits the leaves with the values, and and we will define the type for it. Yes. One moment, please. Yes, I have some spoilers here. So this is our tree, and either we have a branch which has the same tree on the left side, not the same tree, but uh, the instance of the same type, has the value in the middle, and has the same the value of the same type on the right. Also, in this case, it doesn't mean that the order is actually not important here. It's just for us to read it easier, and for now it doesn't mean that this will appear on the left, on this in the middle, and this on the right. Those are just arguments, and they're not rendered and in any way. Those are just three arguments of the function. Or we have a leaf which leads nowhere, but has some value, and that's it. Let's write the renderer for it. Yes. uh, Tree renderer. It renders trees. Now imagine the trees made of geese, and that is what we will eventually do, because why not? Now every our renderer accepts, takes the position, and again in this case we have this argument of the type, and we need to pass the renderer for the inner type, and let's call it the same way. And what we need to just see what's inside this tree, and also use recursion, since we have recursion here in types. We are not obliged to, but it will be useful. So we look what we have in the tree, what we received. If we received the leaf, which is the terminator for the recursion again. So in this case, it doesn't lead into continuing the process. And we also always have to have something like that to terminate. So that's it, and we render the item, the value at a given position in this case. And now we need to cover the branch. So we have the tree on the left. Those are just names again. The value, and the tree on the right. Those are the values that we will render them now this way, that it will look like a tree going from up to down. So we need to render the uh, left part, and we call the same function but with different different position, because we want to move this part of tree a little bit below uh, and on the left side of the central item. So sorry. So the X will be on the left uh, of the central item, and Y will be a little bit below. Let's already replace it with the tree renderer, and for now it will be just unit renderer here. We'll probably need it to move it a little bit. Are we? I'm searching. I have the tree prepared, the tree grown. Yes, we'll also need to move it. So don't. It's unit. Okay, I wrote unit here because I had this function like this, and it is the same. We need to move the central point because our tree will flow from the center of the canvas. So let's imagine some kind of center. So you see the first item already. No, we don't need to move the y-axis probably. We'll see. So let's. This was done just to get rid of a lot of parentheses, which were complicating things. So if I replace all these units with these, it will be the same, but then we get like something weird. So no, we'll make it this way. This is the branch, where left side is the branch, where left side is the leaf with the value. The central part is just value, and the right side is a leaf with the value. And for this branch, the central part is also a value, and the right part is the leaf. So let's continue with our grid renderer. Not the grid tree renderer, sorry. Where are my helpers? They're there. I don't look there a lot, but they make me feel safer. So we render the central item just in the place. Oh, that's why we needed to move it lower. Let's say 19, or the item height actually. Yes. it here as well. I think item plus something like just to have the margin between items. So we already have the left part here and the central part. And we do the same with the right part. Just move it after. So here it is, but it's not right because our tree wasn't that balanced, and we had the leaf on the right side, and it is because I forgot I didn't replace this thing. Now it is. There it is. This is the root branch, and this is the left branch with the items here, and that's it. Let's make it. This will be the same as was rendered. And see, with our types we cannot create the tree here. It's only the place for values. Let's change it to the numbers. And so here we will have 1, here we will have 2, here 3, here 4, here 5. So that's it. And as well, we may do different things like maybe renderer, int renderer, and now we need, for example, this will be nothing, and here we will have to have the just value, here just 2, here just 3, and just 5 here. So we lost that item, or we may get it back with just 4, and have nothing here. Same way, and we may continue. Let's copy this branch here. We'll keep in the brackets this branch, place it here. Yes, just need to move it this way. So as you see, those are still blocks, and again and again. We may create such tree with recursion, of course, and no, it's the leaf. It's branch where there is a leaf with nothing in the middle, and another leaf is also nothing. So they overlap here. It's not the true tree renderer. We need something smarter. But again, we won't complicate things a lot. So we won't do it. Again, this is the end of the second part. And in the third part, we will use this list renderer to make items rotate and draw circles or maybe even spirals. And then in the next section, I plan to try some animation just to show you the concept of how things go in with time in Elm. So that's it this time. Thank you for your attention. See you next time.